Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the grand question of where everything in the universe is going. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. The question of cosmic motion often sounds impossibly large, as if we need giant telescopes or advanced mathematics just to glimpse an answer. But our journey doesn't begin with galaxies or dark energy. It begins much closer to home, right here on Earth, under your feet, where the ground feels still and secure. It seems solid enough. The floor does not slide away beneath you. Your bed does not rush across the room. Yet, in truth, even in this very moment, you're in motion. Always, relentlessly, and astonishingly fast. Start with something familiar, Earth itself. Our planet spins on its axis once every 24 hours, carrying you in a wide circle without you ever feeling it. At the equator, that means moving at more than 1,600 kilometers per hour, faster than a commercial jet. Where you sit, it may be a little slower, but still unimaginably swift compared to the calmness you feel in your body. We don't notice because everything around us spins together. The oceans, the trees, the cities, the clouds. It is like being on a giant merry-go-round so steady and vast that you forget it's turning at all. Yet that is only the first layer of our restlessness. The Earth does not simply spin, it also loops around the sun once every year. That adds another 30 kilometers per second to your invisible journey. To picture that, imagine circling the entire globe in just over 2 minutes. That's the kind of speed we're talking about, yet we sip our tea and check our messages without the faintest sense of being on a hurtling spacecraft. Of course, the sun itself is no still lighthouse in the sky. It too is in motion. Our star orbits the center of the Milky Way at about 230 kilometers per second. That's nearly 1,000 times faster than the speed of sound. One orbit takes about 225 million years, so the last time our sun was in this same position, dinosaurs were just beginning to stride across the Earth. Tonight, as you listen, your body is being carried through a galaxy's spiral arm, tucked safely inside this great stellar carousel. Even the neighborhood around our sun is shaped by motion. Astronomers have discovered that we live inside a kind of cosmic bubble, a region of lower density gas known simply as the local bubble. It's as though the sun is floating through a cleared out cavity, a quiet neighborhood carved long ago by ancient stellar explosions. Within this bubble, nearby stars are scattered more thinly, like lanterns spread out in a vast dim field. We don't feel the edges, but they are there, stretching dozens of light years across, defining the local texture of our galactic home. When you add all these motions together, the spin of Earth, its orbit around the sun's orbit around the galaxy, you realize that stillness is an illusion. Your body lying calmly in bed is really being whisked through space at hundreds of kilometers per second. You might imagine yourself floating on a raft upon a mighty river. You don't feel the current because the raft moves with it, but step back and the whole landscape is rushing downstream. And then, beyond all these layers of motion, lies another frame of reference, the quiet afterglow of the Big Bang itself, known as the cosmic microwave background. It fills the universe in every direction, a soft and ancient light left over from nearly 14 billion years ago. Against this backdrop, astronomers can measure our true drift. They see that our galaxy, along with all its stars and planets and quiet little observers, is sliding across the cosmic sea at nearly 600 kilometers per second. Even after accounting for local swirls and loops, there remains a residual motion, a leftover drift of about 300 kilometers per second, like the final push of a hidden current guiding our raft downstream. What does this mean for us? It means that no matter how calm your room may feel, you are a passenger in a great celestial journey. Your bed is gliding atop the Earth's crust. The Earth whirls around the sun circles the galaxy, and the galaxy itself slips across the universe's invisible stage. You're always travelling, always carried, even when you think you're resting. It's a reminder that stillness is relative, and that sometimes the gentlest truths are also the grandest. As we settle deeper into tonight's exploration, hold on to that picture. Imagine lying back in your bed, yet at the same time gliding through cosmic rivers and galactic streams. It is a journey with no need for engines or maps, only the patient tug of gravity and the quiet unfolding of time. And in this restless but beautiful motion lies the beginning of our story, where all of this, Earth, Sun, stars and galaxies, is ultimately heading. When you think of the Sun, you might picture a great steady beacon fixed in the sky, its light spilling out evenly in all directions. To us on Earth, it feels like the Sun is the anchor of our lives, unmoving, reliable, the centre around which everything else turns. And in one sense that is true. Our days, our seasons, our calendars all pivot on its presence. But in the wider galaxy, the Sun is no anchor at all. It is a traveller, a wanderer threading its path along a spiral arm of the Milky Way. Imagine for a moment the Milky Way itself. Not the flat disk you might see in photographs, but a sweeping island of stars more than 100,000 light-years across. At its centre lies a bulge of stars and dust, and in that heart, a supermassive black hole. The disk curls outward in long arms like ribbons of starlight wound around the core. Our Sun, with its planets and moons, is just one tiny bead within this pattern, orbiting in a broad lane known as the Orion Arm, and orbit it does. Right now, this very second, the Sun is hurtling around the galaxy at nearly 230 kilometers per second. That's about 800,000 kilometers every hour, far faster than anything we could ever build. At that speed, you could zip from New York to Tokyo in less than a minute, if only there were a highway connecting the two. Yet despite this astonishing pace, everything feels still. We feel no wind rushing past, no vibration beneath our feet. We ride along with the Sun in perfect synchrony, unaware of the speed beneath our calmness. This orbit is not a short trip. One lap around the galaxy takes about 225 million years. When dinosaurs roamed the Earth, the Sun was halfway through its last circuit. In the time since, entire species have risen and vanished, mountains have grown and worn away, seas have opened and closed, all while the Sun continued its slow, steady sweep along the galactic road. In fact, over its lifetime of 4.6 billion years, our star has completed roughly 20 laps. The galaxy is not a stage it simply sits upon. It is a racetrack, and we are all permanent runners. But what is this vast orbit guided by? Astronomers discovered that the stars and gas in the galaxy rotate faster than they should, if only the visible matter were pulling them in. Something unseen must be adding to the gravity. We now call it dark matter. It forms a great invisible halo around the galaxy, shaping its rotation, sculpting the path of the Sun and all its neighbours. We don't know yet what dark matter truly is, but without it, our galactic orbit would not make sense. You might think of it like the hidden structure of a house, the beams and framework you never see, but which hold everything in place. And this journey takes us through regions with their own stories. Our Sun is currently travelling through what astronomers call the local bubble, a cavity in the galaxy about 1,000 light-years across, carved long ago by the shock waves of exploding stars. You might imagine it as a neighbourhood in the galaxy that was blasted clear, leaving behind thinner gas and a more transparent view of the stars. It's as if the sun and its planets are floating through a long emptied room, one that still carries the echoes of ancient violence, though now it feels quiet, almost gentle. Every so often, the sun passes close to spiral arms denser with stars, gas and dust. These passages may have played roles in Earth's history. Some scientists speculate that as the sun moves through thicker regions, comets may be nudged from distant reservoirs, occasionally plunging toward the inner solar system. Others suggest that bursts of nearby supernovae might once have influenced Earth's climate, or even the course of life. The galaxy is not just a static backdrop, it is a changing environment, and our orbit is a long voyage through shifting scenery. And while all of this sounds vast and distant, there is something profoundly personal about it. Because you too are on this journey. Every human who has ever lived, every story that has ever been told, every child who has ever looked up at the night sky has been carried along this same path. You are right now a passenger on a starship that requires no fuel, no navigation, no crew, just the simple, enduring force of gravity. It carries us forward, round and round, across the ages. If you want to feel this motion, you cannot, of course, step outside and sense the wind of our galactic race. But you can imagine it. Picture yourself standing in a quiet field at night, the stars stretched above you. Imagine that as you breathe slowly, the ground beneath you is not fixed but flowing. The field, the horizon, the entire Earth and Sun are gliding sideways through the universe at hundreds of kilometers each second. The stars above are not stationary lights. They are fellow travelers on their own paths. Everything is moving, everything is drifting, like fireflies carried on invisible currents of air. And there is comfort in that image. We're not adrift by accident. Our orbit around the Milky Way is stable, steady and ancient. It will continue long after we're gone, a ceaseless rhythm in the vastness. The sun is not lost. It is tracing a curve defined by the mass of countless stars and the quiet weight of unseen matter. Like a bead sliding along a groove, it follows the path carved out by the structure of the galaxy itself. So tonight, as you lie in your bed, you might feel still, you might even feel grounded. But remember that you are also in motion. You're sharing in the grand journey of the sun, orbiting the galaxy at breathtaking speed through neighbourhoods sculpted by stars that lived and died long before us. You're part of this voyage, and you will remain so, quietly gliding as the story of motion stretches on. So far, we've traced the restless layers of our home, the spin of the Earth, the yearly orbit around the sun, and the sun's sweeping path through the Milky Way. Each step revealed that what feels still beneath us is anything but still. Yet even these are only the opening measures of a much larger symphony of motion. Beyond the scales of planets and galaxies lies a quieter stage, a kind of universal background against which all these movements can be measured. That stage is the afterglow of the Big Bang itself, the cosmic microwave background. Imagine it as the faint light left behind after the universe's birth, stretched and cooled over nearly 14 billion years until it now appears as a soft radio hum filling all of space. It is everywhere, in every direction, as steady and patient as the night itself. To astronomers, this background acts like a cosmic grid, a reference frame that doesn't belong to any single star or galaxy, but to the universe as a whole. When we look closely at this background, it is not perfectly even. It has a subtle pattern, a dipole, meaning one side looks slightly warmer and the opposite slightly cooler. That difference comes not from the fabric of the cosmos itself, but from us. It is the signature of our own motion. The Milky Way, and all of us with it, are moving through this ancient light at about 600 kilometers per second. You can think of it like riding through mist on a bicycle. The mist itself doesn't blow, but as you glide through it, droplets gather on your face, thicker in the direction you're heading, thinner behind you. In the same way, the microwave background reveals the direction of our cosmic ride. But there's more hidden here. Astronomers know how to account for the motion of the Earth around the Sun and of the Sun around the galaxy. When they subtract those away, a residual motion remains, about 300 kilometers per second. It is as if, even after peeling off all the obvious layers of drift, something deeper is still pulling us onward. We can't feel it directly. We don't sense the tug, but the numbers, gently and consistently, tell us it is there. This idea that the universe itself provides a preferred frame of rest is both humbling and comforting. In our everyday lives, we measure speed relative to something nearby, the road beneath a car, the ground under our feet. In the universe, expansion itself becomes the ultimate yardstick. Galaxies that follow this expansion, simply swept along by the stretching of space, appear at rest relative to the background. Any deviation from that smooth drift becomes what astronomers call peculiar velocity, a charming term for the individuality of each galaxy's path. Our galaxy's peculiar velocity is a reminder that the cosmos is not perfectly uniform. It has structure, dense regions that tug, empty regions that repel, and a fabric that carries us in complicated streams. Think of it like a great river delta. Most of the water flows steadily toward the sea, spreading evenly. But within that general flow, there are eddies, whirlpools, little currents that swirl and tug you sideways. Our motion relative to the microwave background is one such eddy. We are not simply drifting with the tide of expansion. We are being pulled, nudged, guided by deeper structures we have yet to fully see. And this brings a curious realization. Even when we define the broadest, calmest frame of all, the expansion of the universe itself, we still find that we are not at rest. There is always another layer of drift, another hidden push. Stillness is a kind of mirage, and motion the underlying truth. What does this mean for us, lying quietly in our rooms, eyes growing heavy as the night deepens? It means that you are part of an endless journey, measured not just by the rising and setting of the sun, not just by the galactic orbit of our star, but by the gentle slide of our entire galaxy through the very afterglow of creation. You are, without knowing it, a participant in a voyage that began when time itself began. The thought could be dizzying, but it can also be grounding. Because even though we are moving so quickly, hundreds of kilometers each second, the universe itself provides a reference point, a reminder that our story has context. Against the backdrop of that ancient light, we can measure where we're going and perhaps eventually where we will end up. So tonight, as you rest, imagine yourself lying beneath not just the stars, but beneath the faint glow of the first fire of the cosmos. Imagine that glow as a quiet blanket stretched across the sky, and feel yourself carried smoothly beneath it, along with billions of galaxies, each drifting in their own peculiar way. We're all rafts on this vast current, and the microwave background is the quiet surface that lets us see which way we are truly headed. And that is where our story now turns. If we know our motion against the universe's deepest backdrop, then the next question is, what exactly are we moving toward? What hidden attractors lie ahead, and what silent voids shape our course? To answer that, we must step beyond our galaxy and into the wider map of the cosmic landscape. But before we leap so far, it's enough for now to hold this truth gently. We are not still, and we never have been. Even in our most restful nights, we are gliding through the ancient light of creation, part of a motion that carries us all. As we drift outward from our own galaxy, our eyes are drawn to the great companions that share our part of the cosmos. Among the countless lights scattered across the night, one stands apart, not because it is the brightest star, but because it is not a star at all. To the naked eye it appears faint, just a smudge of light barely visible in a dark sky. Yet that smudge is a galaxy, and not just any galaxy. It is Andromeda, our nearest large neighbour, and it is woven into the very future of our own. If you were to look up on a crisp autumn night in the northern hemisphere, you might see Andromeda rising. Without a telescope, it looks like a pale cloud. With binoculars, it stretches out into a faint oval, a glow that seems to drift at the edge of your vision. And with modern telescopes, it becomes an island of hundreds of billions of stars, larger even than our Milky Way, its spiral arms unfurling like wings of light. There is something humbling in the thought that every pinprick in that oval is a sun of its own, with planets, moons, and perhaps even living beings looking back toward us. What makes Andromeda even more remarkable is not simply its size, but its motion. Nearly every other galaxy we observe is moving away from us, carried outward by the expansion of the universe. Their light is stretched into redder colours, a redshift, by the swelling of space itself. But Andromeda is different. Its light is not stretched but compressed, shifted toward the blue. Astronomers call this a blue shift, and it is the sign of a galaxy not retreating but approaching. The measurements are clear. Andromeda is rushing toward us at about 296 kilometers per second. It's curious to think that something so distant, 2.5 million light-years away, is still, in cosmic terms, barreling straight for us. The Milky Way and Andromeda are not two ships passing in the night, but two dancers caught in each other's gravity, drawn together across the dark. For much of human history, we did not even know that Andromeda was a galaxy. To early astronomers, it was just a nebula, a fuzzy patch among the stars. It wasn't until the early 20th century, when telescopes grew powerful enough, that astronomers like Edwin Hubble proved it lay far beyond the Milky Way, its own system of stars. That discovery shattered our idea of the universe, revealing it to be vastly larger than our single galaxy. And today, Andromeda has become more than just proof of the wider cosmos. It has become a mirror for our own fate. The idea of two galaxies colliding can sound violent, like cars smashing together. But space is vast, and stars are tiny compared to the distances between them. When galaxies merge, the stars themselves rarely collide. Instead, they glide past each other, their orbits twisted and reshaped by the shifting tides of gravity. Gas clouds, however, do crash, igniting bursts of star formation, brilliant new generations of suns lighting up the chaos. Over billions of years, the two spiral galaxies will blend into a single, larger shape. It is not just theory. Around the universe, telescopes capture snapshots of galaxies in various stages of this dance. The pair known as the mice galaxies, with their long, thin tails of stars flung outward, are one striking example. Another, ARP 220, is a tangled knot of dust and brilliant starburst. Two galaxies caught midway through their merging. In these cosmic photographs, we see hints of our own destiny. The Milky Way and Andromeda entwining, reshaping, and ultimately becoming one. For now, though, Andromeda drifts quietly in the distance, a neighbour we can see but not yet touch. Its light takes over 2 million years to reach us, meaning we see it not as it is today, but as it was when early humans first learned to control fire. It has been approaching all this time, slowly, steadily, its path set by gravity long before human eyes ever looked upward. If you lie back and imagine it, you might picture the Milky Way and Andromeda as two figures across a great ballroom floor. For ages they have spun in their own steps, aware of each other, feeling the pull of the music that surrounds them. Now, after long anticipation, the space between them is shrinking, and the dance is drawing them closer. One day, their orbits will overlap, and the ballroom will echo with the sweep of their embrace. It will not happen tomorrow, or in 1 million years, or even in 100 million. but in billions of years, time so vast that it is nearly impossible to hold in your mind, the approach will become unmistakable, and our night sky will change in ways no poet has yet described. The faint smudge of Andromeda will swell, its spiral arms filling the heavens until our galaxy and theirs are one. And so, in this quiet smudge of light, faint above the treetops lies not only a neighbour, but a prophecy. Andromeda is coming. It has been coming for as long as the Milky Way has existed. And in that meeting, still far beyond our personal horizons, the story of where we are going finds its first great milestone. When we think of two galaxies meeting, it's tempting to imagine a catastrophic crash, like two great ships colliding in the dark. But the truth is far more subtle, and in its own way, more beautiful. Galaxies are vast, delicate structures. They are made mostly of empty space, with stars so small compared to the gulfs between them that direct collisions are vanishingly rare. A galaxy merger is less like a car accident and more like two clouds drifting together, their shapes blending, their currents twisting, until both become something new. And yet, while the stars themselves will mostly pass by unharmed, the encounter will be anything but quiet. Gravity will become the conductor of a chaotic symphony, reshaping the orbits of billions of suns. Gas clouds, those great reservoirs of star-making material, will slam together. Their collisions will compress the gas, lighting sudden bursts of star formation across the galaxies. Astronomers call these starbursts, brilliant fireworks of newborn stars scattered like sparks in a storm. For a while, both the Milky Way and Andromeda will blaze with renewed vigour, as if celebrating their union with a final festival of light. The dance will not end quickly. The first approach will come in about 4 billion years. The galaxies will sweep past each other, their arms pulled into long tidal streams. Imagine ribbons of stars flung outward, looping across the sky like luminous bridges. Then gravity will pull them back again, guiding them into another embrace. This back and forth may repeat several times over the course of billions of years, each pass twisting their shapes further, until eventually the cores merge into one. The timescales involved are almost beyond imagination. From the first encounter to the final coalescence may take 5, even 8 billion years. That is longer than the Earth itself has existed so far. Our planet may not even be habitable by then. The sun will have grown hotter, its increased radiation slowly boiling away oceans and scouring the land. Whether or not anyone is here to watch, the cosmic drama will unfold regardless. Astronomers use computer simulations to peer into this distant future. They model the gravitational pull of billions of stars, the dynamics of swirling gas, the slow ripple of dark matter halos. And what they find is that the Milky Way and Andromeda will likely become a single, enormous elliptical galaxy. Spirals like ours are delicate structures easily disrupted. Ellipticals are the end state, rounder, smoother, reddish in colour because star formation has long since burned out. In time, the new galaxy, sometimes called Milkdromeda in a touch of whimsy, will settle into this quiet form. For a sense of what that might look like, we can turn our telescopes outward and study other galaxies mid-merger. The mice galaxies, with their long tails stretching tens of thousands of light years, give a sense of the graceful arcs gravity can carve. ARP 220, dense with dust and bursting with new stars, shows the fireworks of colliding gas clouds. These cosmic portraits are like postcards from our own future. By observing them, we glimpse what may one day happen here. Now pause for a moment and imagine the night sky of a future Earth, or whatever remains of it. Millions of years before the final merger, Andromeda will no longer be a faint smudge. It will grow larger and brighter, spanning more of the sky than the moon does today. Its spiral arms will stretch across the horizon, so grand that no human word could capture the view. In time, the sky will become a tangle of two galaxies, stars from both crossing paths above our heads. Eventually, the cores will glow side by side, then blend, and the heavens will never again look as they once did. It is a strange thought, isn't it? That the serene sky we know, the Milky Way arching overhead, Andromeda as a faint whisper, represents only one brief snapshot of cosmic time. We happen to live in the in-between, far from the galaxy's birth, but still long before their union. The sky is temporary, just like everything else, and yet there is comfort in this impermanence. The merger is not something to fear. By the time it happens, life as we know it may have already moved on, perhaps scattered to other stars, or perhaps gone entirely. What remains is the knowledge that we are part of a larger story, a story that will continue to unfold long after us. The Milky Way and Andromeda, once separate dancers, across the cosmic floor will embrace and become one. So when you look up at the night sky and catch that faint glow of Andromeda, remember that you are seeing not only a neighbour, but a partner in a slow-motion waltz. The steps are billions of years long, the rhythm set by gravity itself, and the finale will be a union of unimaginable scale. It is not a collision to dread, but a transformation to marvel at, a reminder that nothing, not even galaxies, lasts unchanged forever. Picture the final moments of a long dance. Two figures, once circling each other from across the floor, finally meet in an embrace. Their steps blur, their movements intertwine, and at last they merge into a single, graceful form. That is the destiny awaiting the Milky Way and Andromeda. Their spirals, delicate pinwheels of light, will not survive the chaos of the collision. Instead, gravity will sculpt them into something new, an enormous elliptical galaxy, glowing softly in the dark, its once spiraled arms now dissolved into a smoother halo of stars. Astronomers, with a hint of humour, have given it a name, Milkdromeda. But this transformation will not be sudden. Even after the first encounters, when long tails of stars are flung into space like streamers caught in a breeze, the true blending will take billions of years. Slowly, steadily, the two galaxies will lose their separate identities. Their cores will sink together, pulled by gravity into a common centre. Their disks, once neatly ordered, will scatter into a thickened swarm. It will be a process measured not in decades or centuries, but in spans so vast that continents could rise and fall on Earth while the galaxies are still mid-step. What will this new Milkdromeda be like? To answer, we can look to the skies today, at giant elliptical galaxies and clusters far beyond our own. They're vast, roundish, smooth in appearance, and often tinged with a reddish light. That redness tells a story. Their youthful star-making days are largely behind them. Without cold gas left to form new suns, these galaxies glow mainly with the older, cooler stars that remain. The same fate awaits Milkdromeda. After the bursts of star formation triggered by the collision, the supply of gas will dwindle, leaving behind a calmer, quieter population of long-lived red dwarfs. And yet, even in that stillness there will be beauty. The new galaxy may be dotted with globular clusters, dense swarms of ancient stars that orbit like glittering bees around a hive. The central black holes of the Milky Way and Andromeda, each millions of times the mass of our Sun, will spiral toward one another, eventually merging into a single, even greater dark heart. In their union, they may unleash bursts of gravitational waves rippling through space, like the deep bass notes of a symphony too low for human ears, but real nonetheless. For any distant observer, Milkdromeda will shine as one of the largest galaxies in its region of space. Its halo may stretch hundreds of thousands of light years, a kingdom of stars born from what were once two neighbours. From within, the night sky will be transformed forever. Imagine a horizon filled not just with one arching band of the Milky Way, but with a haze of countless stars so thick and bright that the dark between them nearly vanishes. The heavens will appear more crowded, more alive, more overwhelming than anything our eyes have ever known. On Earth, of course, the view will be quite different. By the time the merger is well underway, our Sun will have aged dramatically. In about 5 billion years, it will swell into a red giant engulfing Mercury and Venus, perhaps even Earth itself. Our oceans will have long since boiled away, the atmosphere stripped, the surface scorched. If any remnant of humanity or its descendants endures, they will likely have found new homes among the stars, watching the transformation of their ancestral galaxy from afar. For us, the story of Milkdromeda is less a prediction of personal fate than a glimpse into the deep continuity of cosmic time, and it is worth pausing here to reflect on that continuity. Galaxies are born, they grow, they change shape, they merge, and eventually they fade. Their lives stretch across billions of years, yet they too are impermanent. We often think of the Milky Way as eternal, a permanent stage for the drama of human life. But in truth, it is only one chapter in a longer book, a chapter that will one day give way to another. The name Milkdromeda is a reminder of this impermanence, a playful but profound acknowledgement that even the grandest structures are not immune to change. There is something soothing in that realization. Our own lives are short, fleeting compared to even the blink of a cosmic eye, and yet they unfold within this vast, evolving story. Every breath you take, every night you look up at the stars, is part of the same timeline that leads eventually to the creation of Milkdromeda. You are connected not just to the present Milky Way, but to its future self, to a galaxy that does not yet exist but already has a place reserved in the unfolding map of the universe. So as we leave behind this chapter of colliding galaxies, let the image of Milkdromeda rest softly in your mind. A giant, serene, reddish galaxy glowing in the dark, a monument to billions of years of motion and transformation. It is the destiny of our home, a reminder that even in the deepest scales of time, change is the only constant. And in that truth lies a kind of quiet reassurance that the universe, like us, is always in motion, always becoming, always moving toward what comes next. Up until now, our story has lingered on the intimate scale, our spinning Earth, the Sun's galactic voyage, and the destined meeting with Andromeda. These motions already feel immense, and yet they are only the prelude to something larger. To understand where everything in the universe is going, we have to keep widening our lens step by step until the full landscape comes into view, and the next step outward is to see how galaxies gather into families, groups, clusters, and beyond. Astronomers sometimes speak of the universe as a hierarchy. A single galaxy is never truly alone. Just as people form households and households form towns, galaxies too cluster together in greater and greater communities. The smallest unit is a galaxy group. Our own home, the Milky Way, belongs to such a group, the aptly named local group. It contains a few dozen galaxies, two giants, the Milky Way and Andromeda, plus a supporting cast of smaller companions like the Triangulum Galaxy, the Magellanic Clouds, and a scatter of dwarf galaxies faintly orbiting like satellites. You might picture it as a small town. The Milky Way and Andromeda are the large town squares, buzzing with activity. The dwarfs are the side streets and corner shops, quieter but still part of the fabric. In this town, the residents pull on each other with their shared gravity, and together they form a recognizable community. But as with any town, there are larger centres nearby, cities that exert their own pull. For us, that city is the Virgo cluster. Roughly 65 million light-years away, it is our nearest major galaxy cluster, containing more than 1,000 galaxies bound together in a dense gravitational hub. To compare, if the local group is a town of a few dozen families, Virgo is a metropolis, sprawling with neighbourhoods of spirals, ellipticals, and irregular galaxies. The Virgo cluster is not just large in numbers, but in influence. It sits at the centre of what astronomers call the Virgo supercluster, a region of space where many smaller groups and clusters, including our own local group, all flow gently toward Virgo's mass. It is as if our little town lies on the outskirts of a great city, connected by highways of gravity. We may never actually reach the downtown, it is too far, and the universe's expansion is pulling everything apart. But we're still caught in its broader gravitational sway. If you could look at the Virgo cluster through a telescope, you would see an assembly of galaxies glowing against the dark, each one a city of stars. At the centre of the cluster lies a giant elliptical galaxy, Messier 87. It is not only home to trillions of stars, but also to a black hole so massive that it became the first ever photographed, its shadow imaged by the Event Horizon Telescope in 2019. This central heavyweight acts like the towering skyline of Virgo, a landmark visible across cosmic miles. And here we can pause for a moment of reflection. Imagine the Milky Way, our whole home, with its billions of stars, as only one speck in a small town. Now imagine that town as just one suburb on the edge of a galaxy city like Virgo. Already, the scales are humbling, and yet this is still far from the end of the hierarchy. Just as cities belong to nations, and nations to continents, galaxies and clusters form even greater associations, superclusters that span hundreds of millions of light years. But for now, keep the picture local and clear. You're lying in bed, feeling still, but in reality, you're a citizen of the local group, a member of a small town in the galactic countryside. Off in the distance lies a city, Virgo, so immense that its gravity tugs faintly on our entire group. We're not on its doorstep, but we can sense its pull like a faint hum on the horizon. There is something grounding about thinking this way. When we look up at the night sky, we see stars scattered randomly, like glitter on black velvet. But beyond that first impression, the universe has order. Stars belong to galaxies, galaxies to groups, groups to clusters, and clusters to superclusters. Each step out reveals another layer of community, another reminder that the universe is not chaos, but structure. And within that structure we can begin to trace the flows of motion, the subtle drifts that reveal where everything is going. So tonight, hold this image softly, the Milky Way and Andromeda together, a town in the countryside of space, drifting gently toward the faint lights of Virgo, a city too far to reach but close enough to feel. It is the next chapter in our restless journey, and it sets the stage for an even grander map, the continent of galaxies we call Laniakea. When you imagine the Milky Way, and even Andromeda beside it, you might think of them as solitary giants wandering through the dark. But galaxies rarely exist in isolation. They gather, cluster, and flow together in ways that mirror rivers winding through a landscape. Just as no stream is truly separate from the watershed around it, no galaxy moves entirely alone. To see this, we must zoom out further, past the scale of the Virgo cluster, into something grander still, a continent of galaxies known as Laniakea. The name comes from the Hawaiian language and translates to immeasurable heaven. It is a fitting phrase because Laniakea is almost beyond comprehension. This vast supercluster stretches over 500 million light-years across and contains about 100,000 galaxies. Our own Milky Way is only one tiny dot in this enormous sprawl. If the local group is a small town and Virgo is a bustling city, then Laniakea is the entire continent, an entire landmass of stars and galaxies connected by invisible currents of gravity. How do astronomers know where the borders of such a place lie? After all, space has no neat fences. Instead, they use the motions of galaxies themselves as the guide. Imagine pouring rain into a landscape. Each drop will roll downhill, tracing the slopes and valleys until it reaches a river. If you map enough raindrops, the boundaries of each watershed appear. Invisible but real, shaped by the pull of gravity and the contours of the land. In much the same way, galaxies flow along the contours of the cosmic landscape, drifting under the combined gravity of clusters and voids. By tracing these flows, astronomers can reconstruct the watersheds of the universe. One of the methods they use is not heavy with equations here, but it is a bit like solving a giant puzzle. They measure the speeds of thousands of galaxies, correct for the overall expansion of the universe, and then ask, which way are they drifting? When these directions are plotted, patterns emerge, streams of galaxies flowing together, like rivers heading toward the same basin. Through this careful mapping, astronomers realize that our Milky Way belongs to one enormous watershed, the Laniakea supercluster. Within Laniakea, 4 great streams of galaxies converge. They branch out across the continent like highways, drawing thousands of galaxies inward toward a common center near the Norma cluster, about 220 million light-years away. These branches are not made of dust or stone, but of galaxies themselves, entire islands of stars tracing invisible roads. To picture it, you might imagine a continent seen from high above, with mountain ranges and valleys channeling rivers toward a central sea. That sea, in this case, is the gravitational heart of Laniakea, and yet Laniakea is not a static map. The borders are defined not by walls but by motion. Just as a raindrop that falls on one side of a ridge belongs to one river basin, and on the other side belongs to another, galaxies on different sides of these invisible divides belong to different superclusters. Our local group, for instance, flows within the branch of Laniakea that points toward the Great Attractor, a mysterious mass hidden behind the dust of our Milky Way. Meanwhile, farther along, the pull of the even larger Shapley supercluster begins to compete. The result is a cosmic landscape full of convergences and rivalries, like tectonic plates nudging continents into new shapes. It's worth pausing here to notice how much this resembles the Earth beneath us. Rivers carve valleys, mountains set boundaries, continents gather watersheds. The universe does much the same, only on scales so large that it defies imagination. The galaxies we see are like the raindrops, and the cosmic web they trace is the unseen terrain. In this way, Laniakea is less a cluster of dots on a map than a dynamic dance, a choreography of motion played out over hundreds of millions of years. For us, tucked into a quiet corner of this continent, the experience is abstract. You cannot look up tonight and see the boundaries of Laniakea painted across the stars, but you can sense it in the patterns, the way galaxies drift together, the way our local group belongs to something larger, the way all roads of motion eventually converge towards certain centers. To know that our galaxy is not just an isolated wanderer, but part of a vast continental structure is both humbling and strangely comforting. Think of it this way. Your home belongs to a street, that street to a neighborhood, that neighborhood to a city, and the city to a continent. In the same way, the Milky Way belongs to the local group, which belongs to the Virgo cluster, which belongs to Laniakea. Each layer adds context, each step outward shows us a bigger picture. And in seeing the bigger picture, we glimpse more of the answer to where everything is going. So tonight, as you drift towards sleep, imagine that you're not just lying in your bed, or even just circling the Milky Way. Imagine instead that you're resting within a vast continental map of galaxies, all of them sliding gently along cosmic rivers toward a common heart. It is a motion so immense that we cannot feel it, but it is happening all the same, quiet, steady, and inevitable. And in the midst of this immeasurable heaven, our little galaxy drifts onward, part of something far greater than itself. Every continent has its landmarks, mountains that rise higher than the rest, valleys that shape the rivers around them. Laniakea, our continent of galaxies, is no different. Within its sprawling streams, there lies a gravitational landmark so mysterious that astronomers gave it a name that sounds almost like a riddle: the Great Attractor. The Great Attractor is not something you can see through a telescope the way you see Andromeda or the Virgo cluster. It is hidden behind a curtain, the dense disk of our own Milky Way. This region of the sky is cluttered with dust and stars that block our view, a blind spot sometimes called the zone of avoidance. Behind this veil lies a gravitational anomaly, a concentration of mass about 220 million light-years away, pulling thousands of galaxies, including our own, gently in its direction. How do we know it is there if we cannot see it clearly? The answer lies in motion. Astronomers measure the velocities of galaxies, how their light shifts due to the expansion of the universe and any extra tugs of gravity. When these motions are plotted across the sky, a strange pattern emerges. Galaxies are not just drifting outward with cosmic expansion, they're also streaming, flowing toward a common region. The current of motion points to the Great Attractor, like leaves caught in a breeze all tumbling toward the same hollow. For a time, this discovery in the 1970s and 80s puzzled astronomers deeply. The pull was clear, but the cause was hard to pin down. Was there a gigantic cluster of galaxies hidden behind the Milky Way's dust? Was there some new, unseen structure? Later studies revealed that the Great Attractor is centered near the Norma cluster, a massive collection of galaxies. But even that does not explain everything. The pull seems too large to be explained by Norma alone. Further surveys hinted that an even bigger heavyweight, the Shapley supercluster, hundreds of millions of light-years farther, might also be shaping the flows. This is where the Great Attractor becomes more than just a single object. It is part of a larger tug-of-war, one node in a web of gravitational pulls and pushes. In fact, calling it a single destination might be misleading. Instead, it is more like a crossroads, where the currents of motion converge, guided both by the Norma cluster's mass and the distant influence of Shapley. For us, though, the name holds power. The Great Attractor. It suggests inevitability, as if all paths lead there. But the truth is subtler. The expansion of the universe is accelerating thanks to dark energy, and that acceleration may prevent us from ever reaching this mysterious landmark. The Great Attractor is a signpost of where our galaxy is currently drifting, not necessarily where it will end. It is a reminder that the universe's story is not written in straight lines, but in flowing currents shaped by competing forces. If you'd like an image to hold on to, imagine a ship at sea. Far ahead glimmers the light of a lighthouse, a beacon pulling your gaze. The currents of the water, the shape of the waves, all seem to nudge you toward it. Yet behind that lighthouse lies an even brighter one, farther away but even stronger. You cannot see it clearly from where you stand, but its presence shapes the entire ocean. The Great Attractor is that first beacon, real, pulling, but only part of a larger map of forces that guide the flow of galaxies. And perhaps this is why the Great Attractor captures the imagination. It represents the sense that even on the larger scales there are destinations, mysteries hidden behind veils, pulling us quietly onward. For the Milky Way, it is a reminder that our local group is not drifting randomly. We are part of a larger flow sliding across Laniakea toward a gravitational center we cannot fully see. Astronomers continue to peer into this hidden zone with X-ray and radio telescopes, which can cut through some of the dust that blinds us in visible light. They are mapping the galaxies of the Norma cluster, tracing the larger streams toward Shapley, and refining the picture of how our cosmic continent is shaped. Each new discovery reveals that the Great Attractor is less a single mountain and more part of a mountain range, a massive structure that blends into the even larger web of the universe. Still, the name endures, and as you rest tonight, you can imagine yourself as part of that flow. Our galaxy a leaf caught in a current, drifting toward a hidden valley we cannot see. It is both humbling and strangely comforting to know that we are part of a story larger than ourselves, carried along by forces that reach far beyond what we can observe. And so, with the Great Attractor, our journey takes a turn. Because just beyond it lies Shapley, the rival heavyweight, and beyond that, the strange influence of the voids, regions of emptiness that push as strongly as clusters pull. To know where everything in the universe is going, we must understand not only the beacons of mass, but also the silent spaces in between, When you first hear the name Great Attractor, it feels final, as if the mystery has been solved, one enormous landmark pulling everything its way. But in truth, the cosmos rarely gives such simple answers. The deeper astronomers looked, the clearer it became that the Great Attractor was not the end of the story, only the beginning. Behind it, farther still, looms something even larger and more powerful, the Shapley supercluster. If the Great Attractor is like a lighthouse hidden in mist, then Shapley is the dazzling city of lights beyond it, brighter and heavier, commanding more of the horizon. It lies about 650 million light-years away, almost 3 times as far as the Great Attractor, and yet it exerts such an enormous gravitational pull that it may dominate the flows of entire regions of the sky. In fact, some astronomers now believe that our motion toward the Great Attractor may only be part of a longer journey, one that is ultimately guided by Shapley's immense weight. What is Shapley, exactly? Imagine a sprawling metropolitan hub on the scale of galaxies. Where Virgo contains about 1,000 galaxies, Shapley holds tens of thousands. It is not a single cluster, but a chain of clusters, strung together like luminous pearls stretching across hundreds of millions of light-years. Within it lie some of the largest galaxies known, each with trillions of stars, surrounded by dense webs of smaller neighbours. In mass, it outweighs the Great Attractor by orders of magnitude, a heavyweight in the cosmic ring. For decades, its existence was hinted at, but only more recently have detailed surveys revealed its full scale. By measuring the redshifts of galaxies in its direction and correcting for the expansion of space, astronomers traced a vast overdensity, meaning an area packed with far more galaxies than the average cosmic field. They began to realise that Shapley was not only real but influential, bending the paths of galaxies far beyond its immediate neighbourhood. Think of it like this. If the Great Attractor were a mountain drawing rivers into its valleys, Shapley is the towering range behind it, so massive that it shapes the winds themselves. We may feel the tug of the nearer mountain first, but the larger forces of the range continue to shape the landscape on scales we can barely comprehend. This realization changes the way we see our own motion. It is not that we're falling directly into the Great Attractor like a stone into a well. Rather, we are part of a complex flow shaped by multiple giants. The Norma cluster at the Great Attractor, the massive heart of Shapley farther beyond, and the counterweight of expanding voids pushing from the opposite direction. The Milky Way's path is not a straight line to a single point. It is a curve, a compromise, a balance between many forces acting at once. If you close your eyes, you might imagine this as a game of tug-of-war, except not with a single rope, but with dozens of cords tied around a drifting boat. Some ropes pull harder than others, some from nearby docks, others from distant shores. The boat does not lurch straight to one place, but drifts along the vector of all these pulls combined. That boat is our galaxy. The ropes are the attractors and repellers of the universe, and Shapley, with its immense size, is one of the strongest cords tugging at us from afar. Even the numbers, abstract as they are, can inspire awe. Shapley may contain a mass equivalent to more than 10 million billion suns. Its brightest galaxies shine hundreds of times brighter than the Milky Way. To gaze upon it through a telescope is to see not one smudge of light, but an entire field shimmering with galaxies, each a city of stars in its own right. From this distance they merge into a diffuse glow, a reminder that even the largest scales are made of countless smaller parts. And yet, despite its grandeur, Shapley is still just one structure among many. The universe is laced with superclusters, filaments, and walls. Some larger still, like the Sloan Great Wall or the Hercules Corona Borealis Great Wall, stretching across billions of light years. But Shapley matters to us in a personal way, because it is close enough and heavy enough to leave its imprint on our own cosmic drift. The discovery of Shapley's influence reminds us that the universe is layered in complexity. What seems like a final answer often reveals itself to be only one chapter in a longer story. The Great Attractor was once thought to be the destination. Now we see it as a milestone, a waypoint on a longer flow whose horizon stretches farther still. And so, as you rest tonight, you might picture our galaxy as part of a slow migration across a continent of galaxies. We're not racing headlong into one city, but drifting across a landscape shaped by many. Shapley is the great capital in the distance, glowing faintly on the horizon, its pull mixed with others, its influence subtle but undeniable. We may never arrive there, but its gravity is already written into our path. In the end, the story of Shapley is not just about where we are going. It is also about perspective. The more we zoom out, the more we realize that no single landmark defines our fate. The universe is not a straight road, but a web, and our journey is shaped by the interplay of giants both near and far. To ask, where are we going, is to accept that the answer may never be one place, but many. It is a question that expands with every step outward, as the map of the cosmos grows larger and the currents of motion reveal ever greater complexity. When we think of motion through space, it is natural to imagine being pulled by planets, by stars, by clusters of galaxies so massive that their gravity bends even the paths of light. Attraction feels intuitive. What is less obvious, though no less real, is the role of emptiness. In the universe, the spaces where matter is scarce can shape motion just as strongly as the places where it gathers. These are the cosmic voids, and they do not pull, they push. A cosmic void is not simply an empty hole. It is a vast region of space, sometimes hundreds of millions of light years across, where galaxies are rare, matter is thin, and density is well below average. Imagine looking down at a sponge. The bright clusters of galaxies are like the solid parts, while the holes are the voids. The cosmic web of the universe is just like that sponge on a scale almost impossible to grasp. Why do voids matter? Because in the expanding universe, emptiness expands fastest of all. Where there is less matter, there is less gravity to hold things together, so voids stretch more quickly, their edges pushed outward by the accelerating fabric of space. In effect, they behave like vast balloons inflating in the middle of the cosmic web, pushing galaxies away from them just as surely as clusters pull them inward. One particular void has proven especially important in shaping our motion: the dipole repeller. Astronomers gave it this name because its presence seems to balance the Great Attractor. While Norma and Shapley pull us in one direction, this vast underdense region pushes from the opposite side, creating the flow we observe. The name may sound technical, but the idea is simple. The universe is not just a stage of beacons tugging us forward, but of hollows nudging us away. Our motion is the result of both, the dance of presence and absence, of light and of shadow. If you would like an everyday image, think of standing in a valley between two mountains. One mountain might draw the wind downhill toward its slopes, while the empty valley behind you channels air outward, away from the low pressure there. Your body is caught between these two currents, pulled on one side, pushed on the other. The galaxy is much the same. We are pulled by clusters, pushed by voids, drifting through the balance of both. The thought that emptiness has agency feels strange at first. We usually think of nothingness as passive, as the absence of action. But on the grandest scales, nothingness can shape everything. Voids carve the large-scale patterns of the universe. They define the walls, filaments, and clusters, just as valleys define mountain ridges. In their growth, they herd galaxies into streams, guide clusters into chains, and influence the direction of cosmic flows. The dipole repeller is not the only void. The local void, for instance, sits not far from our own neighbourhood. It is a region nearly 150 million light-years across, with very few galaxies inside. The Milky Way lies on its edge, and in a sense, part of our motion comes from simply sliding away from this underdense basin. Like water flowing out of a shallow bowl, we are being nudged outward, joining the streams that flow toward denser regions. Voids may not sparkle like galaxies or blaze like quasars, but they are the quiet sculptors of the universe. Their influence is subtle, patient, spread over billions of years, and yet without them the cosmic web would not have its shape. Clusters would not form their familiar chains, walls would not stretch across the sky, and flows would not take their current paths. The push of nothing is as essential as the pull of something. There is a quiet poetry in that, isn't there? That absence has weight, that silence has influence. It reminds us that the universe is not only about what is there, but also about what is not. The stars in your night sky shine because of presence, the fusion of atoms, the release of light, but the vast dark between them shapes the picture as much as the stars themselves. Without darkness, the stars would have no contrast. Without voids, galaxies would have no rivers to follow. So as you drift deeper into rest tonight, imagine yourself not only pulled by the glowing clusters, but also gently pushed by the expanding hollows. Picture great empty chambers of space swelling outward, their quiet expansion nudging our galaxy away. It is a reminder that motion is not always driven by forceful presence. Sometimes it is the whisper of absence that carries us along, and in this balance, pulls from the Great Attractor and Shapley, pushes from the dipole repeller and local void, we begin to see the true map of our motion. It is not one road leading to one destination. It is a network of currents, shaped by the gravity of what is there and the expansion of what is not. The universe itself is both sculptor and stage, carving rivers of motion from the contrast between fullness and emptiness. By now, our story has traced both the pulls of massive clusters and the quiet pushes of empty voids. But there are other whispers in the cosmic landscape, subtler hints, half-confirmed rumours, and echoes from the very dawn of time. To truly ask where everything in the universe is going, we must pause and listen for these fainter signals, because they remind us that the map of motion may stretch even farther than we can currently see. One such mystery is known as dark flow. Around the late 2000s, astronomers studying the motions of galaxy clusters noticed something unusual. Using a clever technique involving the afterglow of the Big Bang, they thought they detected a faint but consistent drift. Clusters of galaxies all moving in the same direction, as if pulled by something far beyond the horizon of the observable universe. It was as though a hidden hand was tugging entire swathes of the cosmos, nudging them in a coordinated stream. The technique they used is a mouthful, the kinematic Sunyaev-Zeldovich effect, but its essence can be understood in simple terms. When hot gas in a galaxy cluster scatters the photons of the cosmic microwave background, it leaves a tiny fingerprint, like the ripple of a pebble disturbing the reflection on a pond. By studying these distortions, astronomers can infer how clusters are moving. And when they did, they thought they saw a pattern, a drift toward a point in the sky near the constellation Centaurus and Vela, suspiciously close to the region of the Great Attractor. The idea of dark flow sparked imaginations. Was there a massive structure beyond our observable horizon, hidden forever from our view, pulling at us with gravity? Could it be evidence of something even stranger? Another universe, brushing against our own? For a time, the idea was both exhilarating and unsettling. It suggested that our map of cosmic motion was incomplete, that we were being drawn by something we could never reach. But science is careful. Later observations, especially from the Planck satellite, cast doubt on the claim. Planck's more precise data suggested that the signal may not be real after all, that what was once thought to be dark flow was simply noise or an artifact of the method. The controversy remains a reminder. The cosmos is subtle, and our tools, though powerful, must always be questioned. For now, the idea of dark flow remains a beautiful possibility, not a proven reality. And yet, whether or not dark flow is real, we know for certain that the early universe left imprints that still shape the way galaxies move today. One of the most striking is the Baryon acoustic oscillation, or BAO. The name may sound dense, but the concept is almost musical. In the hot plasma of the infant universe, sound waves rippled outward through matter and light. These waves left behind a preferred scale, a faint shell of clustering, about 400 million light-years across, etched into the cosmic web. You can imagine it like the frozen ripples left after a stone is thrown into a pond. Long after the water has calmed, the pattern of circles may still be visible in the way leaves drift along the surface. In the same way, galaxies today still arrange themselves in patterns that echo those ancient sound waves. The cosmic web has rings built into it, subtle but real, a fossil record of the universe's first vibrations. Astronomers even give names to these structures. One such shell, sometimes called Helena, wraps around the Bootes supercluster. It is like a great organizing principle, a rhythm set billions of years ago that galaxies continue to follow. These echoes remind us that not all flows are guided by present-day giants like Virgo or Shapley. Some were written into the cosmos from the very beginning, when the universe itself was only a few 100,000 years old. There is poetry in this too. Imagine a vast orchestra striking a single note in the first seconds of creation. That note echoes still, not in sound we can hear, but in the arrangement of galaxies across the sky. Every cluster, every void, every flow is part of that lingering vibration. The Baryon acoustic oscillation is, in a sense, the music of the universe made visible, frozen into the cosmic web like notes etched onto a page. So when we ask where everything in the universe is going, we must remember that the answer is not only about the visible pulls of clusters and the silent pushes of voids. It is also about the echoes of the past, the waves that rippled through the early cosmos, setting patterns that endure billions of years later. We are not just drifting in response to what exists now, but also following trails laid down when the universe itself was young. And here, perhaps, lies a gentle lesson. Our paths are not determined by the present alone. They are shaped by histories, by echoes, by rhythms that began long before us. Just as your own life is guided not only by where you stand today, but by the memories and choices of your past, so too the universe carries forward the imprints of its beginning. The galaxies flow not only toward clusters, not only away from voids, but along the ripples of an ancient song. As you close your eyes tonight, imagine the universe as a great pond at dawn. A stone was dropped into it billions of years ago, and the ripples spread outward. You, your galaxy, all the galaxies you can see are like leaves drifting upon that water, still moved, even now, by the first circles spreading across its surface. The echoes of the beginning are the guides of the present, and they are part of the reason why everything, everywhere, is still in motion. So far, our journey has followed the visible architecture of the cosmos. Galaxies clustering together, superclusters weaving into vast filaments, voids swelling and pushing outward, and echoes of ancient sound waves still shaping the pattern of the sky. All of this gives us a sense of structure, of rivers and basins, of flows that can be mapped and followed. But if we step back to see the universe as a whole, something stranger emerges, something that is less about structures and more about the fabric of space itself. That something is dark energy, and it has quietly rewritten the destiny of everything. For much of cosmic history, gravity was in charge. The universe began hot, dense, and expanding after the Big Bang. Gravity fought against that expansion, slowing it down, pulling matter into clumps that became stars, galaxies, and clusters. For billions of years, gravity seemed to hold the reins. The story was one of gradual deceleration, as though the universe were a ball tossed upward, climbing ever higher but losing speed as it went. Then, around 5 billion years ago, something changed. The universe did not continue to slow down. Instead, it began to speed up. Galaxies that should have been decelerating in their outward drift started to accelerate away. The cosmic ball, instead of slowing at the top of its arc, suddenly began to rise faster. It was as if a hidden engine had switched on, pumping energy into the expansion of space itself. Astronomers first discovered this in the late 1990s, when two teams studying distant supernovae, the spectacular deaths of stars, noticed that these explosions were dimmer than expected. The only explanation was that the universe's expansion had sped up, stretching the light more than anyone had anticipated. The discovery was so shocking that it earned a Nobel Prize. Suddenly, the tidy picture of gravity slowly reigning in the cosmos was replaced by a far stranger image. A universe driven apart by a mysterious repulsive force. We call this force dark energy. The name is less an explanation than a placeholder, a label for our ignorance. We know it makes up about 70% of the universe's total energy budget. We know it acts everywhere, evenly, woven into the fabric of space itself. But we do not know what it is. It could be a cosmological constant, as Einstein once suggested, a fixed energy inherent to space, or it could be something dynamic, an evolving field that changes over time. For now, it remains one of the deepest mysteries in science. But even if we do not understand its nature, we can trace its effects. Since dark energy became dominant 5 billion years ago, it has steadily accelerated the expansion of space. Clusters of galaxies that are not tightly bound together are drifting apart faster and faster. The filaments of the cosmic web, once held together by the combined pull of gravity, are slowly unravelling. On the grander scales, the universe is no longer a place of gathering but of separation. If you'd like a picture, imagine inflating a balloon. At first, you blow air gently and the surface stretches slowly. Gravity plays the role of the balloon's rubber, tugging inward, trying to keep things tight. But then, midway through, an invisible pump takes over, pushing the balloon outward faster and faster. The rubber still pulls, but the pressure inside overwhelms it. That is the universe since dark energy became dominant. Expansion is no longer slowing down, it is racing ahead. And just as in earlier chapters, we can anchor this vast idea in everyday experience. Think of watching clouds drift apart on a summer day. At first, they move lazily, carried by a gentle breeze, but then, almost without you noticing, the pace quickens. The gaps widen, the sky opens, and soon the clouds that once seemed close are separated by great stretches of blue. In the same way, galaxies that once shared a common sky are now drifting apart, their separations growing ever faster under the influence of dark energy. The consequences are profound. It means that the structures we see today, clusters, filaments, superclusters, are temporary. Gravity will hold some things together, the local group, the Virgo cluster, perhaps a few other tightly bound families, but everything else is doomed to scatter, pulled apart by the acceleration of space. In the deep future, superclusters will dissolve, the cosmic web will thin, and each gravitational island will be left in isolation. This is the moment where the story of motion turns from maps to fate. The rivers and basins we traced earlier still matter, but dark energy now controls the sea in which they flow. Its invisible hand dictates not just where we're going today, but whether we will ever reach the places we seem to be heading. The Great Attractor, the Shapley supercluster. These may be destinations on paper, but in practice they are slipping away, carried beyond our reach by the accelerating tide. And so, as you close your eyes tonight, imagine yourself lying beneath a sky where galaxies drift like clouds. You cannot see the hidden engine driving them apart, but you can feel the consequence. Space itself stretching, the distances lengthening, the horizon retreating. It is a strange, quiet truth that the emptiness of the universe is not passive, but active, an agent that decides the future of everything. Gravity may have built the structures we see, but dark energy is deciding how they will end. If you step outside on a still night and look up, the stars appear timeless. The constellations seem permanent, the same shapes that guided sailors and storytellers thousands of years ago. It is easy to imagine that the great patterns of the sky will endure forever, but the truth is that the universe is in motion, and under the influence of dark energy, that motion is speeding up. At small scales, gravity still rules. The Earth holds its orbit around the Sun its path around the Milky Way. The local group of galaxies is tightly bound. Our Milky Way and Andromeda are fated to merge no matter what dark energy does. But beyond those intimate neighbourhoods, the balance tips. For clusters and superclusters, not tightly tied together, expansion wins. Dark energy stretches the fabric of space itself, and with every passing billion years, that stretching accelerates. To picture this, imagine watching a line of cars disappearing into a fog. At first, they drift away slowly, their taillights still visible, red glows fading into the distance, but then the fog thickens and the cars seem to slip faster and faster out of view. No matter how far you walk, you cannot catch them. The road itself is lengthening beneath your feet. That is how galaxies behave under dark energy. They do not move through space so much as space itself grows between them, widening the gaps. This discovery was so surprising because for decades astronomers expected the opposite. They assumed the universe's expansion would gradually slow under the pull of gravity. Perhaps it might even reverse one day, collapsing back into a fiery crunch. Instead, the supernovae surveys in the 1990s revealed the opposite. Galaxies were not slowing but accelerating, as though an invisible wind were pushing them apart. The data could not be ignored, and the idea of dark energy became unavoidable, and the acceleration is not small. Today, galaxies beyond our local cluster recede at ever-increasing speeds. The farther away they are, the faster they slip from us, a relationship called the Hubble flow. At modest distances, that speed is measurable but not overwhelming. But as you extend your gaze, the numbers grow astonishing. A galaxy a few billion light-years away may already be receding faster than the speed of light. Not because it is breaking any rule of physics, but because the space between us is stretching faster than light can bridge. We could send out a signal, a message travelling at light speed, and it would never catch up. That truth is sobering. It means that the visible universe is shrinking, not in size, but in accessibility. Galaxies that we can see today are already crossing an invisible horizon. Their light reaches us now, but any light they send in the future will never arrive. It is like standing on a shore at dusk, watching ships on the horizon. You see them for a while as they sail away, but soon they vanish into the night, leaving only memory. The universe is filled with such departing ships, their sails pulled outward by dark energy. This also means that the cosmic web itself, the intricate pattern of filaments, clusters and voids, will not remain as it is. In the early universe, gravity was still knitting these filaments together, drawing galaxies into chains and walls. But under acceleration, the knitting is undone. Filaments stretch, clusters drift, superclusters dissolve. What seems like a permanent scaffold of the cosmos is in fact temporary, fragile against the push of expansion. And yet, there is a strange gentleness in this unravelling. It does not happen with a bang or a crash. It is silent, patient, measured in billions upon billions of years. To us it feels almost motionless. If you compare the sky tonight with the sky a million years from now, the changes would be almost invisible. But over the span of cosmic history, the changes are profound. The sky we know is fleeting, just one frame in an endless reel. Perhaps the most poignant truth is this. In the far future, observers in the Milky Way, or rather in Milkdromeda, long after our merger with Andromeda, will see only their own galaxy. All others will have slipped beyond the horizon, invisible forever. The universe will appear dark and empty, not because it truly is, but because expansion has carried everything else away. To those future astronomers, the cosmos will seem lonely, devoid of the rich structures we see today. They may not even be able to infer the Big Bang, for the evidence will have vanished over the horizon. So tonight, when you gaze up and see galaxies through a telescope, Andromeda, the faint smudges of Virgo, the glow of distant clusters, remember that you're witnessing a rare window. You are alive in a cosmic moment when the universe is still richly connected, when the great web is still visible, when the galaxies have not yet all sailed beyond sight. You are living in the age of galaxies, the one era when the night sky can tell this story. Dark energy ensures that this era will not last forever, but that very impermanence gives it beauty. The stars and galaxies you see are not just random lights. They are a fleeting arrangement, a chorus singing together for a brief span before the voices fade into silence. And in the quiet knowledge of that, there is something calming, that even the larger scales share the same truth as our lives. All things move, all things change, and the beauty of the present lies in knowing it will not always be here. In the chapters of our story so far, we've spoken often of gatherings. Galaxies collected into groups, groups into clusters, clusters into superclusters. These gatherings give the universe its structure, its skeleton. They are the scaffolding upon which the cosmic web is built. But under the growing influence of dark energy, even these immense structures cannot last. Over time they will unravel, thread by thread, until only the smallest knots remain. To understand why, we need to remember how gravity works on these scales. A cluster of galaxies like Virgo is tightly bound by its own mass. The galaxies within it orbit their common centre of gravity, like bees around a hive. No matter how much the universe expands, the cluster itself will remain intact. The local group too is safe. The Milky Way, Andromeda and their dwarf companions are tied together strongly enough to resist the stretching of space. They will merge and evolve, but they will not scatter. Superclusters, however, are different. They are vast associations of clusters and groups strung together in chains and sheets that can span hundreds of millions of light years. But these associations are not bound tightly. They are more like neighbourhoods spread loosely across the countryside, connected by roads but not cemented together, and roads can stretch. Under the accelerating expansion of space, the filaments linking clusters in a supercluster are drawn taut, then pulled apart until the connections dissolve. Imagine a woven cloth. At first it is tight, its threads holding firmly together. But if you begin to stretch it from all sides, the weave loosens. Threads slip, knots come undone, and eventually the fabric frays. The cosmic web is that cloth. Dark energy is the force stretching it ever outward. And the unravelling has already begun. The Virgo supercluster, which once seemed like our cosmic continent, is not truly a permanent structure. Already astronomers have redefined its borders, folding it into the larger map of Laniakea. Even Laniakea, though beautiful to imagine, is not destined to endure. Its rivers of galaxies which now flow together toward the Norma cluster will not all arrive there. Beyond the local group and perhaps a few neighbouring clusters, gravity is simply too weak to fight the expansion. The filaments will snap and the galaxies will slip away into the widening void. This may feel abstract, but we can ground it in an everyday picture. Think of a family gathering at a park. Everyone arrives together, spreads blankets, and shares food. For a while, the gathering feels whole. But as the day goes on, people drift away. Some head home early, others linger. Slowly, the crowd thins until only a handful remain. By evening, the park is quiet again. A supercluster is like that picnic. For a cosmic afternoon, galaxies share a common space, linked by filaments and flows. But in the long evening of dark energy, the gathering will end. The timescales are immense, of course. Billions of years from now, the Virgo cluster will still exist, its galaxies buzzing around each other. But the broader supercluster, the network of other clusters around it, will have scattered, each retreating beyond the horizon. To future observers, Virgo will no longer be part of a larger structure. It will be an island in a dark sea, cut off from the rest, and so too with us. Our local group will remain intact, but beyond that the lights will fade. The Great Attractor will slip away, Shapley will drift out of reach. The grand rivers of Laniakea will vanish into the night. To those who live in that future, the universe will appear far emptier than it does today. The cosmic web, so intricate and beautiful in our maps, will have unravelled to nothing more than scattered islands of light. There is something bittersweet in this realization. We're alive at a special time, a time when the cosmic web is still visible, when telescopes can trace filaments across billions of light years, when the universe still reveals its grand design. This window will not last. In the far future, the sky will no longer tell this story. It will be quieter, lonelier, stripped of the landmarks that once gave it shape. But perhaps that is part of the beauty. All gatherings, from families to galaxies, are temporary. They form, they flourish, they dissolve. Their impermanence is what makes them meaningful. To know that our place in the cosmic web is fleeting is to appreciate it all the more. Tonight, when you imagine galaxies flowing along filaments, clustering into superclusters, remember that you are witnessing a fragile moment in cosmic history. The weave is still tight, the thread still visible, but the stretching has already begun. And as the weave comes undone, what remains? Only the most stubborn knots, the local group, the Virgo cluster, other clusters scattered across space. These will endure as islands in the great dark ocean, each holding tight to its members, each glowing faintly against the backdrop of endless expansion. The universe will no longer be a tapestry. It will be an archipelago, and we will be one small island among many, drifting in the sea of forever. Imagine for a moment a village by the sea. At first, it feels connected to the wider world. Boats come and go, trade routes cross its harbour, travellers pass through its streets. But over time, the waters rise, the currents shift, and one by one the connections vanish. The boats stop coming. The harbours fall silent. Eventually the village finds itself alone, cut off by an ocean that has grown too wide to cross. This is the fate of our local group of galaxies. Right now, we still feel connected to the broader cosmos. Telescopes reveal streams of galaxies stretching toward the Virgo cluster, flows pointing us to the Great Attractor, even hints of Shapley's distant pull. The map of the universe looks busy and full, with threads linking every cluster and supercluster. But this is only a temporary view, a window that belongs to our particular age. Dark energy, the quiet force we spoke of before, is stretching space so quickly that those threads will not endure. In the deep future, the local group will become an island in a vast dark sea. Virgo, once the bustling city on our horizon, will slip away, its light red-shifted until it disappears entirely beyond the cosmic boundary. The Great Attractor, so mysterious today, will no longer matter to us, because its pull will be outpaced by expansion. Even Shapley, with all its weight and grandeur, will vanish from view. Only the galaxies that are gravitationally bound to us will remain. These are our companions, the Milky Way, Andromeda, the Triangulum Galaxy, and a flock of smaller dwarfs. Over billions of years they will merge and rearrange, eventually coalescing into a single giant galaxy, Milkdromeda. That remnant will be the heart of our island universe, floating alone while the rest of the cosmos slips away. It is strange to think of this isolation. We live in a golden age of astronomy, when the night sky is full of clues to the universe's origin and fate. By studying the expansion of galaxies, we can trace back to the Big Bang. By mapping the cosmic web, we can understand the shape of structure. But future astronomers, living perhaps trillions of years from now, will not be so fortunate. To them, the sky will appear nearly empty. No Virgo cluster, no Laniakea, no cosmic web. Only the glowing remnant of Milkdromeda will remain, surrounded by darkness. Without the evidence of expansion visible across the sky, they may never guess the universe's true story. The local group will be cut off, like a village surrounded by an endless ocean. Its residents will have no way to sail across, no way to see what lies beyond. And yet, life within the village will go on. Stars will still rise and set. Black holes will still hum in the dark. Globular clusters will still circle like lanterns. The island will be smaller, yes, but it will still contain richness of its own. We can soften this picture with another metaphor. Think of a library in a quiet town. At first, books arrive from every direction. Shipments of stories and knowledge pour in, and the shelves grow heavy. But then, the supply routes falter. The library is cut off. No new books come. All that remains is what is already on the shelves. At first, that seems limiting, but within those shelves, there are still countless tales to explore. The local group will be that library. No new galaxies will arrive, but the ones already here will continue their long, quiet stories, unfolding across unimaginable spans of time. For us, living today, there is also comfort in this vision. Even as the wider universe fades from view, our little island will hold together. The local group will not unravel like superclusters. Gravity is strong enough here to keep us bound. Andromeda will not slip away. The Milky Way will not vanish beyond a horizon. Our companions will remain with us through collisions, mergers, and transformations long after the rest of the cosmos has drifted out of reach. So, as you settle into the quiet of this night, you might imagine your home not as a speck in an endless crowd, but as a member of a small village surrounded by rising seas. The ships have not yet vanished. The horizon is still busy with sails, but one day, far in the future, the waters will close in and only the village will remain. And in that village, in the Milky Way, in Andromeda, in Triangulum, in the dwarfs, life will continue its patient unfolding. The local group will be our island universe, drifting alone in the dark, and perhaps that is enough. Within it are billions of stars, trillions of planets, countless stories still unwritten. Isolation need not mean emptiness. It simply means the stage has grown smaller, the focus sharper, the light gathered into one place. If you close your eyes and imagine the sky billions of years from now, it will look profoundly different from the one we know today. Andromeda will no longer appear as a faint smudge on the horizon. By then, its stars will have streamed into ours, its spiral arms interwoven with the Milky Ways. The two galaxies will no longer be rivals in a long-distance approach, but threads of the same fabric, stitched together into a single luminous form. This new galaxy, often called Milkdromeda, will be our home. From the outside, Milkdromeda will resemble the giant elliptical galaxies we see in other parts of the universe. Smooth, rounded, and reddish in hue. Spirals are delicate structures like whirlpools in a river easily disturbed by mergers. Ellipticals, on the other hand, are the end state of many collisions, calmer in appearance, but filled with the relics of past upheavals. The beautiful spirals of both the Milky Way and Andromeda will fade into memory, replaced by a softer glow. Yet within, the galaxy will still teem with billions of suns, their lives unfolding over spans of time that dwarf our own. But even within this merged remnant, change will continue. Over trillions of years, the stars themselves will begin to scatter. Every close encounter between two stars, though rare on human scales, exchanges a tiny bit of energy. Slowly, over unimaginable spans of time, these encounters act like shuffles in a dance floor, with some stars nudged inward toward the centre and others flung outward toward the edges. This process, called gravitational relaxation, will eventually thin out the population. Some stars will be kicked free of the galaxy entirely, wandering into the dark between islands, like sparks carried off by the wind after a fire. Others will fall inward, toward the central black hole. Today, the Milky Way has a black hole of about 4 million solar masses, while Andromeda hosts one perhaps 10 times larger. When they merge, the result will be a single supermassive black hole of staggering size. Around it, stars will orbit in complex swirls, some gradually spiralling inward, others slingshot outward. The centre of Milkdromeda will be a place of both quiet gravity and occasional drama, where entire suns can be swallowed or shredded by the darkness. Outside the core, smaller companions will continue their own stories. Globular clusters, those dense spherical swarms of ancient stars, will orbit like bees around a hive, their members slowly evaporating into space. Dwarf galaxies, once satellites of the Milky Way and Andromeda, may be consumed or torn apart, leaving behind streams of stars stretched across the sky like faint ribbons. Black holes and neutron stars, the remnants of massive suns, will roam like invisible wanderers, drifting for trillions of years through the galaxy's outskirts. It is easy to think of this far future Milkdromeda as static, frozen in its final form. But the truth is more dynamic, though at a pace almost too slow to imagine. To us, years are long. To galaxies, they are heartbeats. Over 1 trillion years, the outlines of Milkdromeda will shift, stars scattering outward like embers blown from a long fire. Each one carries a history, a fusion engine that once lit a world, now drifting alone into the dark. And yet, despite the scattering, Milkdromeda itself will endure. The gravitational heart will remain bound, even as its edges thin. Its central black hole will persist, a monument to the merger of giants. Its surviving stars, long-lived red dwarfs glowing dimly but steadily, will provide light for trillions of years more. They are the quiet survivors of cosmic time, tiny compared to the sun, but enduring in ways our star cannot. To imagine this future, think of an old bonfire. At first, the flames leap high, brilliant and noisy. Then, as the night deepens, the blaze softens. The logs collapse into coals, glowing with a deeper red. Sparks rise into the sky, carried away by the breeze. Eventually the fire becomes a bed of embers, warm but fading. Milkdromeda will be that bonfire. The spirals of today are the early flames. The scattering of stars will be the sparks, and the dim dwarfs glowing at the end will be the embers, the last warmth of a galaxy long past its prime. This vision can feel lonely, but it can also feel strangely peaceful. We often think of change as destruction, but in the universe, change is the rhythm of being. Stars are born, they shine, they die. Galaxies collide, merge, scatter. Nothing is wasted, only transformed. The atoms of our bodies were forged in ancient stars. The atoms of those stars will one day scatter into space again, to be remade into something else. Even in the far future quiet of Milkdromeda, the cycle will continue in its own slow, steady way. So as you drift tonight, picture yourself not in the Milky Way as it is now, but in Milkdromeda as it will be. Imagine a night sky where the familiar constellations are gone, replaced by a haze of countless merged stars. Imagine globular clusters glowing faintly, black holes moving silently, and ancient dwarfs flickering like coals. It is not a sky of loss, but of transformation, a reminder that even in isolation, even after billions of years, the universe still writes new chapters. Imagine the glow of a campfire as the night stretches on. At first the flames are tall and bright, painting the trees and faces around it with golden light. Then, gradually, the logs collapse inward. The blaze softens, sparks drift away, and the fire becomes a bed of glowing embers, still warm, still alive, but dimmer than before. Eventually even the embers fade, leaving only a faint smoke curling into the darkness. This is the future of the stars in our galaxy, and in every galaxy. For billions of years, the Milky Way and Andromeda have been factories of stars. Clouds of gas collapse, ignite, and form brilliant suns. New generations replace old ones, weaving the fabric of starlight we see when we look up at the sky. But star-making requires fuel, cold clouds of hydrogen and helium, and over time, that fuel runs out. Already, star formation in the Milky Way is slowing compared to its youthful past. After the Milkdromeda merger, bursts of star formation will flare for a time, sparked by colliding gas clouds. But even those supplies will dwindle, and when they do, the universe will grow steadily darker. The first to disappear will be the massive stars. They live fast and burn bright, consuming their fuel in only millions of years before collapsing into black holes or neutron stars. These stars, the blue giants, are the bonfire's roaring flames, beautiful but fleeting. As time stretches forward, their numbers will dwindle until only smaller, cooler stars remain. The survivors will be the red dwarfs. These tiny suns, far smaller than our sun, burn their fuel with extraordinary thrift. A red dwarf can shine not for billions, but for trillions of years. Long after the sun has swollen into a red giant and faded away, the red dwarfs will still be glowing steadily, their dim lights sustaining whatever worlds may remain near them. They are the embers of the cosmic fire, glowing softly in the great dark. Alongside them will be the remnants of stars already gone. White dwarfs, stellar cores left behind after the outer layers drift away, will fill the galaxy. They shine only faintly, slowly cooling as their heat leaks into space. After tens of billions of years, they will fade into black dwarfs, cold, dark husks, invisible against the night. Neutron stars, and black holes will also linger, silent monuments to the violence of stellar death. As the aeons unfold, the galaxy will grow quieter. The bright blues and yellows of new stars will vanish. The sky will no longer blaze with the richness we see today. Instead, it will glow faintly red, lit mostly by long-lived dwarfs. Then, as even these ancient embers fade, the night will darken further. The era of starlight will end, replaced by a quiet of a different kind. But this fading does not happen with drama or catastrophe. It is slow, gentle, like the dimming of a lamp. If you lived within Milkdromeda in those distant times, you might not notice the change in a single lifetime. Generations could pass, and the stars would still shine. It is only across the vast canvas of trillions of years that the fading becomes complete. And even as starlight fades, motion continues. Stars scatter across the galaxy, globular clusters evaporate, black holes merge, planets drift. The cosmic dance does not stop, it only grows quieter, more subdued, as the stage grows darker. To anchor this vision, imagine yourself sitting by a fire at the end of a long night. The wood has burned away, the flames are gone, but the warmth still lingers in the ashes, and the faint glow carries memory of what was once bright. That is the galaxy's future, a memory written in remnants, glowing softly in the shadows. It may sound melancholy, but there is also beauty in this image. The universe is not rushing to a violent end in this scenario. It is exhaling, settling, winding down. The fireworks of the early cosmos, the blazing stars, the crashing galaxies, were its youth. The long twilight of red dwarfs and white dwarfs is its old age, slower, calmer, filled with patience. And in that patience lies a kind of peace. Even in darkness, the atoms forged in stars will endure. Carbon, oxygen, iron, the elements of life will remain scattered across space. Perhaps they will never recombine into living beings again, or perhaps they will, in ways we cannot yet imagine. But the story of those atoms will continue, drifting quietly in the silence of the expanding universe. As you let your own eyes close tonight, imagine the cosmos in that distant era. The sky is not black, but tinged faintly red. dotted with tiny embers glowing for their last trillions of years. Around you drift husks of white dwarfs, the shadows of black holes, the faint arcs of scattered stars. It is not a frightening place. It is simply quieter, gentler, slower. The universe, after all its restlessness, seems to come to rest. When people hear the phrase heat death of the universe, they often picture something dramatic, a fiery collapse or a sudden ending. But the reality is quieter, gentler, and far more patient. Heat death is not an explosion. It is not destruction in the usual sense. It is the slow dimming of a great symphony, the music of the cosmos softening note by note until only silence remains. The idea is simple in principle. The universe, like any system, trends toward equilibrium. In the beginning, there were contrasts everywhere, hot and cold, dense and thin, bright and dark. Those contrasts drove change. Gravity pulled matter together into galaxies and stars. Nuclear fusion lit the stars. Collisions triggered bursts of light and heat. But over time, those contrasts fade. Energy spreads. Temperature evens out. The universe becomes uniform, bland, unable to fuel new structures or events. Imagine pouring cream into coffee. At first, there are swirling eddies, curls of white mixing into black, dramatic differences that catch the eye. But after a while, the coffee turns the same shade of brown. The drama is gone, replaced by sameness. The universe is the same way. Once, it was full of swirling contrasts. One day, it will be flat and even, a lukewarm blend stretched across endless space. In this future, galaxies will continue to drift away from one another. Beyond a certain horizon, they will vanish entirely, their light stretched until it can never reach us. The local group, or whatever remains of it, will be alone. Within it, stars will fade as we've already imagined, red dwarfs glowing for trillions of years before finally cooling into black husks. Black holes will dominate, swallowing what remains of stars and clusters. Even black holes, however, are not eternal. According to Stephen Hawking's insights, they radiate faintly, leaking energy over unimaginable timescales. A black hole with the mass of our Sun would take about 10⁻⁶7 years to evaporate, far longer than the current age of the universe. The giant black holes at the hearts of galaxies will last even longer, up to 10 or 100 years or more, but even they will eventually vanish, dissolving into the faint glow of radiation. As all of this unfolds, the universe will grow colder, temperatures will fall toward absolute zero, motion will slow, no new stars will form, no new galaxies will gather. The great structures of today will be gone, replaced by an almost featureless expanse. It is not fiery chaos that awaits us, but the hush of stillness. The phrase heat death can sound frightening, but perhaps it is better to think of it as the universe going to sleep. A fire burns brightly when it is young, but when the logs are spent, the flames die down. The ashes remain warm for a while, then cool completely. The campfire does not explode or collapse. It simply rests. The cosmos is following the same path, an old fire growing quieter as its fuel runs out. If you'd like another image, picture an orchestra playing a great symphony. In the beginning, the music is loud, filled with trumpets and drums. As it continues, the music softens, the violins linger, then fade. Finally, only a few notes remain, soft woodwinds, a single flute, and then even those stop. The concert hall falls silent, not with violence, but with peace. The heat death of the universe is that silence. Of course, these timescales are far beyond comprehension. We measure our lives in years, our histories in centuries, our civilizations in millennia. The age of the universe itself, 14 billion years, already feels impossible to hold in the mind. But the times leading to heat death are trillions upon trillions upon trillions of years. They stretch farther than any number we normally use, farther than any metaphor can carry. It is eternity in all but name. And yet, there is comfort here. The universe is not racing to destruction. It is not threatened by some sudden catastrophe. Its fate is one of patience, of slow unwinding, of gentle fading. If you imagine yourself lying in bed tonight, you might think of your own body resting, your breathing slowing, your mind easing towards sleep. That is the universe too, exhaling after an age of motion, drifting into a long, still slumber. So when we ask where everything in the universe is going, one possible answer is towards silence. Not a terrifying silence, but a profound one. A silence where every star has burned out, every galaxy has faded, every black hole has dissolved. A silence where time still ticks, but with nothing left to mark it. A silence that is not empty, but complete. And maybe, in that silence, there is a kind of beauty. After all the noise and brilliance, after all the collisions and births, the universe will have found its balance. A balance so perfect that nothing more can happen. It will be, at last, at rest. The idea of heat death paints a picture of the universe fading slowly into stillness, a patient unwinding that stretches across unimaginable spans of time. But there is another possibility, one less gentle, more dramatic, and yet still fascinating to imagine in the quiet of night. It is called the Big Rip, a future where not even atoms survive. The Big Rip begins with the same observation that led us to dark energy. The universe's expansion is accelerating. But what if dark energy is not constant? What if it grows stronger with time, its repulsive push increasing as the universe ages? In that case, acceleration would not just carry galaxies apart, but would intensify until even the most intimate bonds could no longer hold. Gravity would lose. Then the forces that hold galaxies, stars, planets, and even atoms together would surrender. Imagine pulling on a thread. At first, the cloth stretches a little, but the weave remains. Pull harder, and the threads begin to separate. Harder still, and the fibres themselves start to break apart. That is the logic of the Big Rip. Expansion stretches the cosmic fabric until the very fibres of reality cannot endure. Astronomers can map out the sequence. At first, galaxies far beyond our neighbourhood would slip away, as they do in the heat-death scenario. Then, billions of years later, expansion would grow so strong that even clusters like Virgo could no longer stay bound. They would dissolve, their galaxies carried, apart. Closer to home, the local group would begin to feel the strain. Milkdromeda itself would unravel, its stars pulled away from each other, the galaxy smeared into emptiness. Then the scale shrinks. Stars would no longer hold onto their planetary systems. Planets would drift free, torn from their suns. A little later, stars themselves would break apart, their nuclear bonds overwhelmed. And then, at the final moment, even atoms would be ripped to shreds, their protons and neutrons separated, their very structure undone. The universe would not fade into silence. It would end in disassembly, every bond severed, every pattern dissolved. If this sounds violent, it is worth remembering that it would still unfold slowly on human scales. Galaxies would unravel billions of years before stars broke apart. Stars would fail millions of years before atoms themselves were torn. To a creature alive in those times, if any could exist, the process might still feel gradual, a horizon of destruction approaching step by step. Only in the final moments, perhaps the last minutes or seconds, would the pace accelerate to something sudden. It is also worth noting that the Big Rip is not certain. It depends entirely on the nature of dark energy. If dark energy is truly constant, the universe will head toward heat death. If it grows stronger, then the Big Rip becomes possible. Right now, our best measurements lean toward constancy, but the door remains open, if only a crack. Science is honest that we do not yet know. To bring this abstract possibility closer, imagine sitting in a house by the shore. At first, the tide rises gently, lapping at the steps. Then slowly the water creeps higher. Over time, it seeps into the walls, then the beams, until the house itself begins to fall apart. Finally, even the stones of the foundation are swept away, carried into the sea. The house is gone, not because of a sudden blow, but because the tide never stopped rising. The Big Rip is that tide on a cosmic scale. There is something haunting about this vision, but also something strangely calming. Because even in this end, there is no malice, no catastrophe in the human sense. The universe simply follows its rules, carrying motion to its logical extreme. The smallest bonds surrender, not out of violence, but out of inevitability. If you hold the thought gently, it can even feel like poetry. Picture galaxies stretching like taffy, stars drifting apart like sparks, atoms dissolving into their simplest pieces. The universe, once woven so tightly, unwinds completely, returning everything to a state of pure freedom. There are no prisons, no bindings, no constraints, only endless expansion, carrying every particle away from every other. Will this happen? We cannot say. Perhaps dark energy will remain constant, leading to the slow hush of heat death. Perhaps it will grow, leading to the unbinding of all things. Or perhaps the truth is stranger still, waiting for us in discoveries yet to come. For now, the Big Rip is a possibility, a story the cosmos may or may not choose to tell. And as you lie here, listening to the quiet, you might imagine both futures, the slow cooling of a cosmic fire and the final unwinding of every bond. One ends in silence, the other in disassembly, but both remind us of the same truth. Nothing is permanent, not galaxies, not stars, not even the atoms in our bodies. Everything moves, everything changes, everything eventually lets go. The future of the universe, whether it ends in the slow hush of heat death or the final unwinding of a Big Rip, shares one common thread: unimaginable time. The spans we speak of here are not billions or trillions of years, but numbers so vast they leave even our largest metaphors straining. And yet, it is worth pausing to imagine them, because they remind us just how long the story of motion really is. Begin with the end of starlight. By the time the last red dwarfs fade, the universe will already be trillions of years old. 1 trillion years is 1,000 billion years, more than 70 times the current age of the cosmos. To us, that number feels eternal, but in cosmic terms it is only the beginning of the end. After the last stars cool into black dwarfs, the universe enters what astronomers sometimes call the degenerate era. It is a time when the only luminous objects left are the occasional flares of white dwarfs colliding, or the sparks of matter spiraling into black holes. The universe will be a place of remnants, husks of stars, lonely planets, cold dust, and dark giants. But even these remnants will not last forever. Black holes, once thought eternal, are now understood to fade through Hawking radiation. Over inconceivably long timescales, they leak energy into space, like ice cubes slowly melting in a vast ocean. A small black hole might vanish in 10 to almost 67 years. A giant black hole, millions or billions of times the mass of the Sun, could last up to 10-100 years. That number is so large it resists imagination. If every atom in your body were used to count a year, you would not even begin to approach it. And yet even that number is finite. Eventually the black holes will be gone, their darkness replaced by the faintest trickle of radiation. When the last black hole evaporates, the universe will be unimaginably old, so old that words like ancient no longer have meaning. What remains is called the dark era. There will be no stars, no galaxies, no black holes, only particles drifting through expanding space. Photons of radiation, stretched to such long wavelengths that they carry almost no energy, will drift endlessly. Protons themselves may decay, breaking down into lighter particles, until even atoms no longer exist. At that point, the universe will be an ocean of almost nothing, a thin mist of particles spread so far apart that they may never meet again. Time will still pass, but with nothing left to mark its flow. Clocks, if any, could exist, would tick on without purpose. It is an eternity of silence, where motion continues but meaning does not. This vision can feel lonely, but it can also feel profoundly humbling. It reminds us that permanence is not the rule of the cosmos, but its opposite. Everything we know, stars, galaxies, atoms, are temporary patterns, brief dances against the backdrop of forever. Even black holes, which feel eternal in our imagination, are only chapters in a much longer book. And yet, perhaps that is not a reason for despair. There is beauty in the idea that the universe is a story told in movements. The blazing youth of stars, the steady adulthood of galaxies, the long twilight of remnants, and finally the silence of rest. To know that even the mightier structures yield to time is to understand that change is the most universal truth of all. If you want an anchor for this vision, think of a clock. Not the kind on your wall, but a clock that endures beyond civilizations, beyond continents, beyond even the Earth itself. Imagine a clock so patient it counts not hours but eons. Its tick is the decay of a proton. Its tock is the fading of a black hole. It keeps time long after the sun has gone, long after the galaxies have scattered, and still it ticks, marking an eternity where no eyes remain to read it. That is the clock of the universe in its final ages. Perhaps, in this stillness, there will be no witnesses, or perhaps there is something beyond our theories, something that revives the story in ways we cannot yet guess. Some physicists wonder if new universes may bud from the old, if the silence of one cosmos becomes the seed of another. We cannot know. What we can say is that the trajectory of motion, as we understand it, leads to solitude. And in that solitude lies a final lesson. We, alive in this moment, are not just fragments of matter in motion. We are consciousness witnessing a rare chapter. The chapter when the universe is rich with galaxies, when stars still shine, when the cosmic web is still visible. Compared to the lonely eternity that awaits, our present is a moment of astonishing abundance. The sky above you tonight is crowded with light. It is full of stories the future will not remember. So let that image soothe you. The universe, trillions upon trillions of years from now, reduced to a quiet sea of drifting particles. No galaxies, no stars, no planets, only silence. And yet, the silence is not emptiness. It is completeness. The story has been told. The notes have all been played. What remains is the long, gentle rest that follows the music. And so, after wandering through the layers of motion, from the spin of the Earth to the sweep of the sun, to the merging of galaxies, the pull of clusters, the push of voids, and finally the long horizon of dark energy, we arrive at the end of our journey. What began with restlessness ends with quiet. What began with blazing light ends with stillness. The question we asked at the beginning, where is everything in the universe going, has brought us here, to the recognition that all roads eventually lead to isolation. Not isolation in the human sense of loneliness, but in the cosmic sense of separation. Galaxies drift away, superclusters dissolve, starlight fades, black holes evaporate, and even atoms surrender to time. The local group becomes an island. Then, even within that island, stars grow dim and the night grows quiet. Whether through the slow hush of heat death or the dramatic unwinding of the Big Rip, the end is the same. A universe no longer filled with the structures we know today. It can feel overwhelming, even melancholy, to imagine such a fate. A cosmos stripped of galaxies and stars, reduced to silence. But perhaps the point is not the silence itself, but the fact that we are here, now, in the rare chapter when the universe is alive with light. when the night sky is crowded with galaxies, when the cosmic web still stretches from horizon to horizon, when the evidence of beginnings is still written across the heavens, waiting to be read. Think of yourself lying beneath that sky tonight. Above you, stars burn with energy released from the fusion of atoms. Beyond them, galaxies drift, their light stretched across millions of years. And farther still, clusters and superclusters weave their patterns, tugged by gravity, pushed by voids, sculpted by the ancient ripples of the Big Bang. All of it is happening right now. You are alive in a universe still brimming with motion, still full of stories to tell. That is a privilege that future ages will not have. And that perhaps is the true answer to our question. Where is everything going? Towards silence, yes. Toward isolation, yes. But also toward meaning in the present moment. The fact that you can sit here, listening, imagining these scales of time and space, means that the universe has already done something extraordinary. It has created consciousness capable of asking, of wondering, of tracing the map of motion even as it drifts along with it. So rather than dwelling on what will vanish, we can choose to marvel at what exists now. The constellations that glow overhead, the faint smudge of Andromeda, our partner in a future dance, the shimmering of the Virgo cluster on the horizon, the knowledge that we are part of Laniakea, the immeasurable heaven, flowing along rivers of galaxies, the comfort that even as dark energy pulls everything apart, the local group will remain bound, a small village surviving as the seas rise. The end of the universe is not something to fear. It is too far, too patient, too beyond the scope of our lives. Instead, it is something to hold softly in the imagination, like a bedtime story with a quiet closing. The details, the black holes evaporating, the protons decaying, the stars fading, are not threats. They are verses in the poem of time, a poem that has no need of a sharp ending, only of a final rest. So let the last image be this: the universe as a great symphony. It began with a thunderous opening chord, the Big Bang, followed by crescendos of starbirth, the swelling harmonies of galaxies, the gentle counterpoint of clusters and voids. We are listening now during the middle movements, where the music is rich, layered and full. But someday, far beyond our reach, the symphony will quiet, the notes will soften, the themes will fade until the hall is filled only with silence. And in that silence, the music will still exist, not in sound, but in memory, in meaning, in the fact that it was ever played at all. And so, we've reached the end of tonight's exploration. Whether your eyes are still open or you're already drifting somewhere between waking and dreaming, thank you for being part of this journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it is enough simply to be present, to know that the universe is vast in motion and temporary, and that we, small as we are, have the chance to marvel at it while the lights are still shining. Sleep peacefully, wherever and whenever you may be,